pre-calculus students, and welcome to lesson 3.2 on finding equations. We'll be finding equations of exponentials, logarithmics, and logistics. So we're going to start with logarithmic equations here first as a review from previous courses and from previous years. Let's just look at this first box and we'll start working our way through the material. You may have remembered from the past, when we solve logarithmic equations, we had y equals log base b of x is our general form for a logarithm. We're going to always deal with in this course when the b value, our base is positive. Our x also must be positive. We're not going to have any negative numbers inside the parentheses here. And then depending on what else works out, we could get a positive or negative for the y value. But what we did is learn to convert back and forth between a logarithmic and an exponential. What we do know is that if you have a logarithmic form, we can transform it into this b to the y equals x form. And that's what that's explaining up here. Now, some of the ways you might remember this, your teacher in the past might have talked about the looping method. Oops. And the looping method is where we have something like this: log base b of x equals y. What we do is we kind of loop around like this to rewrite that. So we'd say this is b to the y equals x. That's kind of a way to remember how to transform between a logarithmic and an exponential equation. So we'll get a little practice here just doing that. So we're just going to rewrite this equation. So if we just do that looping method, we'd say this is 4 to the x equals 5. Okay? And then also make sure we can go backwards with this as well too, that if we have this in the, notice this is in that exponential form, to be able to rewrite these in log form. So we can see that that y is in that y spot here. So that's our x equals our log. The base is the base of that exponential. And then the x is whatever that's equal to. So it's just kind of rewriting it back and forth. Okay. We also had some basic log properties we should remember. Simply just saying here, this first one, that if we have log base b of 1, so log base of anything of 1 is 0. And again, you can kind of double check this, as you go through by doing the looping method. So b to the 0 power is 1. So really, it doesn't matter what that base is. Anything to the 0 power would be 1. All right. Here's another property. The second one here is log base b of b equals 1. Because again, this would be b to the first power is just what that value is. We can extend that property to say log base b of b to any power is y. And kind of the way I remember teaching this in advanced algebra is when these two things are the same, your answer is just whatever that exponent is. And the last one is just kind of that reverse, if you do have it in exponential form, if you had b log b of x, that the answer is just whatever that value is right here. Okay. So just some other things about logarithms from the past. Common logarithms are base 10. Okay. So we go log base 10 of x. Again, mathematicians would like to write things a little more efficiently. So if we don't have a base, it's always assumed to be 10. It's one of those invisible numbers that we have. Just like with radicals, we've got the square root of x. There's actually a little invisible 2 in there. So same thing here. When we write log of x, there's really an invisible little 10 right there. Again, these are called common logs. And again, if we did, the looping method here, we could say you know, 10 to the y equals x. Or if I, you know, switch these letters around a little bit, you know, it'll be the same thing right here. You know, that y equals 10 to the x if I had the letters switched. Okay. These properties are the same. You know, if I look between these two, this is just any base. This is specifically for the 10 base. So those properties are still really just the same as we go through these examples. All right. So get a little practice here trying to solve some problems using logarithms. So if I had log of 100, this is really like log base 10. So what I would do is I would probably change this to be log base 10 and then try to keep that 100 to be some 10 to some power. So that'd be 10 squared. So now I can use one of the properties that I've used up above there, that if these two things are the same, the answer is just that exponent. Same thing here. I'd rewrite this as log base 10. This thousands down the bottom, so I know that's going to be a negative exponent, and there's 3 zeros. This is actually 10 to the negative 3. So again, the bases are the same. The base and the number are the same. So our answer is just that exponent. Do the same thing here with this one. Again, realizing that radicals can be written as rational exponents. I'd write this as log base 10 of 10 to the number on the inside goes on top, number on the hook goes on the bottom. So it'd be 10 to the 1/5. So my answer here is just 1/5. And this one is that last property up above here. So this is actually a little base 10 there. So our answer is just this 6. And continuing to practice some problems here. We're going to solve this little simple logarithm. So again, maybe I put the little 10 down in there so I can do the looping method. Say this is 10 to the 4th equals x. So this is 10,000 is what the x value is. Okay. Continuing to practice some more of these. Again, I'd say this is log base 10. So log base 10, and I'd write the 100,000 as a 10 to some power. 1, 2, 3, 4, 5 zeros. So again, those are the same. So my answer is just that exponent. Same idea here. Again, I'd have this as log base 10 and write 1 over 100. This is down at the bottom, so I know it's got to be a negative exponent. So it's 10 to the negative 2, because 10 squared is 100. Final answer here is just negative 2. Okay. Again, same idea, same properties as if they're natural logs. Because again, remember now, natural log is the same thing as log base e from the past. So I could really just go back here and rewrite each of these problems, you know, as log base e of 1. You know, so this could be log base e of 1 equals 0. So again, the same properties hold here. You know, so this would be log base e of e is 1. Log base e of e to the y would equal y. And then this would be e log base e of x. So again, you see that number and base are the same. So my answer is just whatever is in that log. So same idea doing these properties. So when I look at this, I'm looking at this as log base e. E to the square root is really e to the 1/2 power. So again, those are the same. So my answer is just 1/2. Same thing here. I could change this ln to log base e. These would be the same. My answer is just 5. And again, this one would be e log base e of 4. So again, when those are the same, the answer is just that number. All right, we get some more practice here. And again, I would just change that ln to log base e. This e to the 3rd square rooted could be written as e to the, again, the number on the inside goes on the top of the fraction, the number in the hook, which is a 2, goes on the bottom. So again, those are the same. So my answer is just 3/2. This one's a little more involved. Got a little bit more work to do on this one. So what I would do, again, I'd write this as log base 7, and this would be 1 over, and again, since I want some kind of base of 7, I'd probably write that as the 4th root of 7 squared. Because 7 squared is 49. That way I've got 7s here that I can start matching up. And then just got to play around with this a little bit to get that so it's just 7 right here. All right. So I see this as 1 over, and then this would be 7 to the 2/4, or I could say 7 to the 1/2. Now, if it's down on the bottom here, I could bring that up to the top and make the exponent negative using our properties of negative exponents before. This would be negative 1/2 because if it's positive on the bottom, it's negative on the top. Now I've got those things the same. My final answer will be negative 1/2. All right, let's keep moving through and continue talking about our logs. And so there's kind of 3 places x's can be. So there's 3 ways to solve. So we could have like an x, we're taking the log of that x. Could be trying to find, the log of a base in some number, or I could actually be trying to find the base. So there's kind of 3 places where we'd have some unknowns that we'd be willing to look for. So again, just kind of rely on those properties, rely on what you know when dealing with the log properties. So really, honestly, with this first one, I'd probably just make that a base 10, and then I could just do the looping method. Make that 10 to the negative 5 equals x. And negative exponent means bring it down to the bottom. And then this would be 1 over 1, 2, 3, 4, 5, 0. So 1 over 100,000. Here, this is, again, probably just using the looping method. Let's go back through here. Let's say this is 4 to the y equals 16. And then looking at 4 to what power is 16? Well, 4 squared equals 16. So this y equals 2 in this case. And again, using the looping method here, I just loop back around here, always starting with that base. I'd have b squared equals 81. Then I take the square root of both sides to solve this. And I'm only going to write the positive number because, again, back for the rules, we don't have negative numbers in the base here. So realistically, mathematically, I got a plus or a minus negative 9. But I'm only going to use that positive one. So really, that negative 9 is kind of an extraneous solution. So we only write b equals 9. So get some more practice here. So again, what I would probably do is I would look for a way to write 8 as 2 to some power. Because then I could get the base and the number here to be the same. Well, 8 is 2 to the 3rd. So my answer is just 3. Here, again, that's the last property in the logarithms. I write this as e raised to the log base e, because that's what ln is, of 2. And again, when those two things are the same, the answer is just right there. So that's 2. All right, then we got the properties of logarithms, which you've dealt with in the past. And really what I want you to remember is when we're multiplying inside, we can split this apart as addition. So just kind of remember that as when you're multiplying, it really becomes addition of the logs. Just like when we're doing exponents, when we're multiplying, say I've got x to the squared, x to the 3rd, I'm multiplying here, but to get that answer, we just add those exponents. So the answer is x to the 5th. So that's kind of that same idea, just in reverse, that if we're multiplying, we can split those apart as 2 different logs and add them. Well, same thing with division. If I'm dividing, just like if I was dividing, say at x to the 5th over x to the 3rd, again, we would just subtract from top to bottom and get our answer. So same thing here, we're dividing, we're actually going to subtract the 2 logs, split them apart. So it kind of looks like here, if I look at multiply and addition, they're really kind of just rotating that symbol here, just taking away the 2 dots to kind of remember that's what we do. And there's the power rule, which simply says that if I've got a log base of something to some exponent, what I could do is I could just bring that exponent out front. Okay. So if I write that just a little bit bigger here, this is log base b of r to the c. So what I know I can do then is I can just bring this out front and write that as c times the log of b times, or log of b of r, I should say. Well, those properties help us simplify logs. Now, if I look at this problem here, I've got 3 logs, and I'd like to be able to simplify this and write it as a single log. So understanding the properties here will help me get that together to be able to write that as 1 log. So what I see here is I see a number out front. Well, I can use that last property over here kind of in reverse. If it's out front, I can bring it back on top as an exponent. So I know I could bring this up there and make this log x squared. And this would be minus, take that 3 and bring it on top there. So it would be minus log of y to the 3rd. Same thing here. And that as plus log of z to the 4th. And then knowing that minus is a division, again, I can just read left to right. It's like order of operations. When I've got just addition and subtraction left, I work left to right. So if I'm combining those 2 pieces, I would have log of x squared, and then it'd be divided by this y to the 3rd. And then because it's plus, I'd be multiplying, so it'd be z to the 4th. That way now I've got it written as 1 log. Well, we can actually do it in reverse as well. I'll try to break this apart here. So this, when I look at this first part, this is this log a to the 5th, and if it's divided by, that means it's minus all of these pieces on the bottom. So it'll be log of b to the 3rd, and now that's times, so that's times here, so this would be plus log of the square root of c. So you notice I went minus all of this because it's divided by all of this. All right. I can continue to simplify this a little bit and bring in those exponents back out front. So I'd have 5 log of a minus 3 log of b plus, now square root of c is really like c to the 1/2. So I could bring that 1/2 power out front. All right, that is log c. This should be fine to leave it like this, but you maybe want to distribute that negative and have this as 5 log a minus 3 log b minus 1/2 log c. All right, continuing on, there's another formula for logarithms called the change of base formula. Kind of getting to be a little bit of an outdated formula, seeing that we've got technology that can kind of do some of these problems for us a little quicker, but it's still a good property to know and to be able to use. Okay. What this basically is saying is, like, if I've got log base b of x, what I can do is I kind of split this up. If I read, this one's kind of a little bit lower, the b is a little bit lower than the x. What we can do is we can just write this as log of x divided by log of b. Oops, I kind of wrote that a little too low because it's not in the base. It's a log of b. Okay, so again, I just kind of see this one is higher than this one, so it should be higher than that one in the fraction. And again, you could write any base you want down here. I just chose to use base 10 or use these as common logs. If you wanted this to be log base 7, unless it had to have this one to be log base 7 as well. So again, I'll kind of show you why. You can shorten you up in the formula with using the formula, because kind of the old way of evaluating this log base 3 of 10 to find out what that is, you'd have to go through the looping method. So you'd end up with 3 to the y equals 10. And this would be kind of an interesting problem to do because 3 to some power doesn't come out to be exactly 10. I mean, 3 squared is 9, so I know this is a little bit more than 2, but I'd have to try to figure out how to solve that. And anytime we're trying to solve for a variable in the exponent, what you would do is you would end up logging both sides. So you go log of 3 to the y equals log of 10. And then we could use some of our properties to solve this by bringing that y out front and write this as y times the log of 3 equals the log of 10. And then I divide both sides by log of 3. So I would have y equals log of 10 over the log of 3. And then you could type that in your calculator and get that answer, which would be a little over 2. But if you know the formula, you wouldn't have to go through all this work. You could just get right to that answer. So if you saw this, you see, oh, that's the 10 is a little higher than the 3, so you just write this as log 10 over log 3. And again, I always choose to use 10 as the base here because it's just easier. And then you type that in your calculator to get your answer, which would be a little over 2. All right, let's do a little review of the graph transformations and look at kind of how things get moved around. What I want to just talk about is the graph of a logarithm. You should have that from our parent graphs that we studied back in chapter 1. But your general logarithm will go through 1, 0, and kind of come up like this and then curve like that. Okay. So we're looking at just kind of describing how these graphs would be moved. So sometimes, if we start with this f of x equals ln of x, okay, might help us to do some of our graph or log properties to rewrite this. So I'd have g of x equals, bring this 2 out front, so I'd have 2 times the ln of x. And if you remember out front, if the number's out front here, that affects whether it's vertically stretched or squished. And if it's out front here, it's away from the y value that's over here. So we do it as is. It's not inside parentheses there. So what this is a vertical stretch of 2 times. Okay. I'm going to skip over B for a second and go to C because I think it just flows a little bit better here. Because this one here, you notice it's a little bit different. This one here had the number out front, so it's a vertical stretch. This number is inside with the x. So remember now, when we think it's inside with parentheses with the x value, we got to think opposite. Okay, so this isn't a stretch. It's actually going to be a squish. Because it's in with the x, it's actually a horizontal. So this is a horizontal shrink or squish. I don't care which word you use. Or horizontal shrink of 3 times. So it shrinks 3 times. You could also say it's 1/3 the size as well. Now this one here is a little bit more complex because we're going from a natural log to a common log. So really, this is like base 10 right there. Okay. So if we use the property we just talked about here, that change of base formula, we could write this as h of x equals log of x over the log of 10. And earlier I said it really doesn't matter what you change those bases to. I just chose to use 10, but as long as the bases match, that's fine. So really, I could actually convert this, and instead of writing it as base 10 here when I use the formula here, maybe conveniently what I do is I do log base e of x all over log base e of 10. And because it doesn't matter when you do the change of base theorem, what you change the bases to, as long as they're the same. So really this is then natural log of x, because that's what log base e is, over the natural log of 10. And if I rewrite this just a little bit differently, I write this as 1 over the natural log of 10, just kind of pull that out front, times the natural log of x. I can then compare this to the original graph. You can see this is now out front 1 over natural log of 10 is a fraction between 0 and 1. So this is actually a vertical shrink of 1 over ln of 10. Just like this one here, was a vertical stretch. It's a number bigger than 1, so it stretches it. This is a number between 0 and 1, so it shrinks it. So a little more complex, as you saw. And then we're just kind of doing some matching of graphs and kind of understanding what's going to happen with each of these. So if I look at letter A here, it's the natural log of 2x, so that's on the inside. So that should be a horizontal shrink of twice as much. So it should still have the graph that, again, normal logarithm graphs do this and go through 1. So this one here should, if it's a horizontal shrink of 2, well, now instead of going through 1, if I horizontally shrink it, that's going to be twice as much. Now it's going to cross at a half. So that's this one right here, because 1's right here, half is right in there as it comes through. So this one here is letter A. Letter B, negative log base 4 of x. So again, if that negative is out front, that's a flip across the x-axis. All right. So that would be this one that's right below it here. Just flips, because normally it goes again like this. So it's come through here. Well, now it just flips over. So now it's going to come from the top and go through 1. So that's letter B. Letter C, or maybe even actually letter D, might be a little bit easier because I see that negative out front. So if I'm kind of doing some process of elimination, again, it's got to be one that starts at the top and goes down. So this graph here is supposed to be just, I don't know why this other one is there. The graph is supposed to be this darker one. But if I'm flipping this one, again, that's a flip across the x-axis, and then this is inside. So that's it's a number. You got to think opposite. So it's half, but really, I think opposite would be twice as much. So it's going to move. It's going to be a horizontal stretch of twice as much. So now it's going to be, instead of going through 1, it's going to go through 2, but it's also flipped upside down. So that's letter D. And then this one's got to be C. And what was this one wasn't supposed to be there. It was supposed to just be this graph right here. And as it come through, that's supposed to be 1 right there. It was kind of coming through the half part. And that's what this one is here. So it's, again, that horizontal shrink by twice as much. This part right here, that 0.05, you want to kind of work through this problem, kind of rewrite this a little bit with that change of base theorem. You can actually have log of 2x all over log of 0.5. So this is really, actually, if you want to write that a little better, it's kind of like log of 1/2, which this would be actually log of 2x all over log of 1 minus log of 2. Right? And if I continue this, we'll give myself a little more room. This would be, this log of 1 is just 1. So that's 1 minus log of 2. So this is really like, I'm sorry, this would actually be 0, my bad. This would be 0 because it's base 10 to what power is 1, so that'd be 0. So this is really like log of 2x all over negative log of 2. And if I'm trying to bring that up front, this is f of x equals 1 over negative log 2 times log of 2x. So again, this is a vertical, this would be a vertical shrink, and then also flipped because there's that negative. So that's why when I look at letter D, it's a, that's why it's upside down, because the negative piece, it's been shrunk vertically, but also, I'm sorry, I'm doing letter C here. This is why it's been pushed, vertically shrunk, and then it's also horizontally squished as well too. So that's why it's coming in there before 1. The negative flips it upside down too. So that's a little more complicated one. I don't think we're going to get a lot of those, but just thought I'd throw that out there for you. All right, continuing on, we're going to look at exponentials and be able to determine formulas for exponentials. Let's just kind of just really get right into the problem here and demonstrate this. What we know is if we're looking at exponential functions are always in the form y equals a times, I'll put in parentheses here, b to the x. So knowing that, we want to be able to find an equation given 2 points that make up an exponential. So way back, if you think about this, we used to do this with lines. Given 2 points, find the equation of a line. Here now we're doing finding 2 points, find the equation of the exponential. So we got to rely on this, knowing that that's the form for an exponential. So we kind of do the same thing that we would have done for lines, is we're going to take each point, put it into the equation. So if I do that, this is my x, that's my y. So I would say 4 equals a times this b value raised to the x. B to the 0 is just 1, so this is a equals 4. So that's good. I've got the a value for this equation that I can eventually put into here. So when I start to write this, y equals 4 times. Now I've got to figure out what that b value is. Well, I need another equation. So let's put these in. So I'd have this would be 12 equals a times b to the first. Well, I already got the a value here, so I can stick that in there. So this is 12 equals 4 times b to the first is just b. Divide both sides by 4, my b value is 3. And there's my equation, my exponential equation, formed by using these 2 points. They're not all that easy. Some involve a little bit more work, so let's take a look at another one. But same process. Let's take a point, create the equation for this. So again, 32 is my y value, a times b to the x power, which is -1. Let's do it with this other one too. So just have those all set up. So this would be 2 equals a times b to that x value, which is to the first. So we got 2 equations, 2 unknowns. Probably best to solve this with substitution. So I'll kind of rearrange this, rewrite this one here. This is 32 equals a, and then if it's -x1, I can bring it down to the bottom and make it positive. I could clear this fraction just by multiplying both sides by b. So multiply this by b and that by b, that cancels, so I get 32b equals a. Well, I solved this for a, so I can substitute this into this a over here. So I'd have 2 equals 32b, and then times that b to the first. This is really 2 equals 32b squared. Divide by 32. So 2 divided by 32 is 1 over 16. And if I square root both sides, I get b equals 1/4. I actually get positive and -1/4. But again, we're talking about, we don't have negative numbers inside there for that b when we deal with exponential growth or decay problems. So there's my b value. So I'm going to write that equation, y equals, my b value is 1/4. To get that a value, I got to put that in here. So 32 times 1/4 is 8. So there's my a value. right, so just some more review here. We've got exponential population model. They give us this formula here, this P of t equals P sub 0, which is our initial population, times 1 plus r raised to the x power. So that r is just that rate of growth or the rate of decay. So it's positive. This r value is positive if it's growing. It's negative if it's decaying. So really what we're looking at is really just this exponential form where that a is our initial value and that b is that rate of growth. So if that b value is bigger than 1, it is growth. If that b value is between 0 and 1, it is decay. Because if I subtract off 1, if that r value is decay, I'm going to subtract that off of 1. So again, that's a little review from the past. Let's take a look. If I look at this first problem, maybe rewrite this just a little bit clearer here. Maybe write that as the y equals form. So this is y equals 786,543 times 1.021, and they have that raised to the t. All right. So here is where I'm going to identify that whether it's growth or decay, it's above 1. So when I look at how much what that r value is, that r value is 0.021. That's what I've added to 1. So that's why it's growth. But we generally like to report rates of growth as percents. So then I'll move that 2 places. So the rate of growth is 2.1%. If I look at this one, I don't know what that symbol is there. There's our initial value. Here is our b value, so it's below 1. So we got to look at, what was this? What was that r value? So I'm going to go 1 minus 0.9858, and I would get what 0.0142. So that's what that's actually, that's what I'm subtracting off. So as a percent, that's 1.42%. So that is my rate of decay. All right, looking at some more problems here and how we're going to use that. Let's write, it says determine the exponential function with initial value of 10. Okay, well, that's easy to start off with. Y equals 10, there's my initial value. And if we're increasing, okay, that's growth. So when I'm going to add that to 1, it's going to be 1 plus something. And if it's 5%, I'm going to add that as a decimal. So that would just be 1.05 to the x. So there's my equation, my exponential function. And kind of we're learning how to practice solving some of these problems. The question says, when is the population equal to 5,000? Well, that's what that y value is. So I've got to solve this. So 5,000 equals 10 times 1.05 to the x. Probably easy just to start off here, just divide both sides by 10. So you'd have 500 equals 1.05 to the x. And this is where the log properties come in. Because if we're solving for an x in the exponent, you should log both sides. So log of 500 equals log of 1.05 to the x. I can then bring that out front. And this would be log of 500 equals x times log of 1.05. And then I can just divide both sides by that log of 1.05. So x equals log of 500 divided by log of 1.05. So you can just type that in your calculator. And I believe if you do, it's approximately 127 or something like that. So question says, when is the population equal to 5,000? Well, again, this is per year. So it's 127 years from now. Right? So whatever the year is, 2020, add 127 years to it. So 2147. All right, some more practice, just writing equations. So we're going to find an exponential equation. So again, we know exponentials are on the form y equals a times b to the x. It's got an initial value of 20. That goes in for the a spot. And it's going to decrease. It's decreasing at a rate of 17%. We've got to go 1 minus 17%. That's 83% here. X. Again, now the X will stand for every year. Same thing here, exponential equation. So we'll go y equals a times b to the x. Initial value is 20, so that's the a value. And then we're increasing at a rate of 17%, so that's 1 plus 0.17. So that'd be times 1.17 to the x power. Again, the x stands for per year. All right. Well, sometimes they don't give you the percentage. They just tell you that it's doubling or it's tripling. So again, just realizing doubling is multiplying by 2, tripling is multiplying by 3. A half-life would be a half, or if we're talking about quarters, 1/4. Okay. So how does that look in a problem? Well, again, if I'm finding an exponential equation, that's y equals a times b to the x. Initial value is 20. And then if it says it triples every month, well, that's 3. And the x. So the x here again stands for each month. All right. So that's kind of important to realize that for the context of problems is make sure you understand, that's not always years. It depends on whatever time unit they're defining. So here, exponential equation, y equals a times b to the x. Initial value is 20. So we put 20 in there. And this has a half-life, so that's half to the x. And again, realize here now x stands for every 5 months. So every 5 months. So that's where you'd have to look like if it's 10 months, well, then, so here, let's do 10 months. What you'd have here is y equals 20 times 1/2. So 10 months would be 2. So after 10 months, that's 2 of these intervals. Okay? If it was like 7 months, this would be y equals 20 times 1/2. In 7 months is a little more than this 1 and a little bit more, or you can just think of this as 7/5, just like this one would have been 10/5, which is 2. Okay? So again, I'm just really emphasizing, just make sure you watch how they're defining the time for that. Okay, so there's logarithms, there's exponentials. Lastly, we've got our logistics. Yes, our logistic equations here. So that's just remembering again that our basic form, we've got it right here. So it's just that that y equals, and that c value is our limit to growth. That's the maximum it can grow to. And then down at the bottom, we have 1 plus ab to the x. So again, if I just kind of write that out a little bit better, y equals c over 1 plus a times b to the x. Now I'm going to emphasize with you, again, this c is the limit to growth. Okay, that's the numerator. The limit to growth is this c value. Okay, it's the maximum sustainable population. I just want to be careful that you don't take what we just did with the exponentials and say that this a value is our initial value. That's not true. That is not true. All right. So we have to look at that in solving the problems, and I'll show you how to do that. So here's just kind of one that's made up here. This is a logistic model, kind of snaking through here. It goes through at 0.5, goes through at 0.5, and also at 310. Okay, so those are 2 points that are on there. So just like the last problem that we did in trying to find a model for this, we're going to use these 2 coordinates and just substitute them into our equation, get 2 unknowns and solve. we also see here, y equals 20, that's our limit to growth right up here. And so that's the highest it's going to get to. So that's kind of the easy thing to start off with, is we just go y equals 20, got that on the top, and then it's 1 plus a b to the x. So now that I got that there, I can use and write two different equations using these coordinates. So I'll take this first coordinate, 5, 0. So 5 is the y value, equals 20 over 1 plus a b, and the x value is 0. Then go ahead and create the second equation using this coordinate. And that's 10 is the y value, equals 20 over 1 plus ab to the x value, which is 3. So I've really got two equations and two unknowns. And so I'm going to have to solve this, and probably the best is by substitution. So if I can solve one for a or for b and substitute in the other, I can get both the a and the b value to go back and put into this equation to find out the exact model for this. So here, I'm probably going to go here because b to the 0 is just 1. So this is really just 5 equals 20 over 1 plus a. I could clear this fraction here. So this would be 5 times 1 plus a equals 20. Distribute this. This would be 5 plus 5a equals 20. Subtract 5 from both sides. So that's 15. So a equals 3. So I've got that piece. Probably good to go and put that into this equation. So I've got 10 equals 20 over 1 plus 3b to the third power. The same thing, I'll just clear that fraction, multiply both sides by that denominator, so I'd have 10 times 1 plus 3b to the third equals 20. I'll just divide both sides by 10 here, so I got 1 plus 3b to the third equals 2. I subtract 1, divide by 3, oops, that's a third. And then take the cubed root of this, so I have b equals the cubed root of 1/3. It's kind of a funky answer there, but that's all right. So that's what I can put in my b value. So my final equation here, I substitute this stuff in, y equals 20 over 1 plus my a value was 3. The b value is the cubed root of 1/3, and that'd be to the x power then. Probably need a little more practice with that, so let's do that. All right, so we got another one here. We got two coordinates on a logistic model. Again, here's our limit to growth. So the maximum value there is 44. So limit to growth. So when I write that equation, I can just start with that. Y equals 44 is on the top, 1 plus a b to the x. And then just use each of these coordinates to create an equation. So I'll use that first one. I have that as 11 equals 44 over 1 plus a b to the 0 power. And I'll use this other equation here to create another, plug that in. So we've got 22 equals 44 over 1 plus a b to the 5th. All right, start here because this one's already gets the b knocked out because it's just b to the 0 is 1. So this is really 11 equals 44 over 1 plus a. Clear those fractions, so multiply each side by that. So 11 times 1 plus a, cleared here, equals 44. Distribute, so you get 11 plus 11a equals 44. Subtract 11. Divide by 11, a is 3. All right. I can put that into this equation here, so I get 22 equals 44 over 1 plus 3 times b to the 5th. You can clear the fractions here, so I have 22 times 1 plus 3b to the 5th equals 44. I probably just end up dividing by 22 here. Now I think that might make it a little bit easier. So that's fine. I go 1 plus 3, a little different than what I did over there, just a different method. So that's 1 plus 3b to the 5th. If I divide by 22, that's 2. Subtract 1. Divide by 3. And then I could take the 5th root of both sides. So that b equals the 5th root of 1/3. So if I rewrite that final equation, that's just y equals 44 over 1 plus the a value, which is 3, times the b value, which is the 5th root of 1/3, that'd be to the x power. Yeah, this is all new, so let's keep practicing. Let's get a couple other practice problems here. And just make sure we understand the language here. So this says find a logistic model if the initial amount is 10. So again, what I want to do is make sure you understand that when we talk about the initial amount, you're not just putting 10 in for that a value. So we got our regular logistic equation model here of c over 1 plus a times b to the x. I'm not telling you that this a value is 10. I'm telling you the initial amount is 10, which means that that's the y-intercept, that's 0, 10 is my initial amount. Here it says the limit of growth is 40, so I know that's the c value. And here's another point that it passes through. So I've got 2 points, 0, 10, and 120 that it goes through. So it's that same process. Just start with this equation, y equals, again, my initial growth is 40, and then 1 plus ab to the x. And this is due to equations of putting these points in. So this first one here, put 10 in for y. So then I get 40 over 1 plus a, b, and then the x value is 0. So if I keep solving this one, 10 equals 40 over b to the 0 is 1, so this is just 1 plus a. Multiply both sides by 1 plus a, so it clears the fraction, so I get 10 times 1 plus a equals 40. Now you can either distribute this, or I'd like to actually just divide both sides by 10, so I just have 1 plus a equals 4, subtract 1, a is 3. If I do it with this other point, put this into the equation, I get the y value is 20 equals 40 all over 1 plus a b to the x value, which is 1. Okay. I also know this a value is 3. So 20 equals 40 over 1 plus 3 times b to the first, which is just b. Clear the fraction here, multiply both sides by 1 plus 3b, so I get 20 times 1 plus 3b equals 40. Again, I prefer just to divide by 20, so I just have 1 plus 3b equals 2. I subtract 1, get 1, divide by 3, b is 1/3. So we're in the final equation here, y equals 40 over 1 plus the a value, which is 3, times my b value, which is 1/3. That's to the x power. All right, try one more here. And maybe what we should do here is pause the video and then have you try it and come back and see if you got it right. All right, and hopefully this is the answer you got. Is 20 over 1 plus 7/3 times the cube root of 1/7 to the x power. So there's the work here if you need to look at that and go through, double check your work. Obviously pause the video and go through it. So there you go, there's lesson 3.2, kind of a long one, but covers a lot of material. Simply, the whole idea was able to find equations, logistic, logarithmic, and exponential. Thank you, we'll see you in the next video.